Good. So, I gave you the I gave you the broad introduction, but chapter 1. I hope that all of you have the textbook now. But chapter 1 does a pretty broad overview of the basics of how we think about E&M. So one of the things is the concept of the field, right? So you know that, classically speaking, you got some charge here, you got some charge there. These are, two charged objects, and there's going to be a Coulomb force that is going to be attractive or repulsive based on whether these charges are like or are opposite, right? So opposites attract and likes repel. Now that was hang on a second. Now that's a perfectly legitimate way of thinking about electricity and magnetism, but it's not really the most useful way of looking at it. So what we usually do is we'll say, well, there's this field generated by this charge, and then we place this charge into that field, and this is of course our electric field, and we evaluate the electric field as a function of position and time based on whether this thing is moving or not. That might give you a different answer. And then by the time this electric field line hits this point, you can ask yourself, okay, what is the force that is acting on that charged object? And then you just take its Q times E, right? And the point is that the field is the thing that mediates the interaction. Hang on. Okay, so it's perfectly legitimate to do electricity and magnetism based only on Coulomb forces and Lorentz forces, but it's really not the most insightful. So as you know, the electric field and the magnetic field, they play a central role in this subject, right? So there's an electric field that is in general some function of position and time, and then there's the magnetic field that is some function of position and time. Now, for the longest time, they were just considered to be useful concepts, just a way to kind of take apart the problem. So rather than talking about pairwise interactions, you can just calculate some kind of a field, electric field, magnetic field, and then place your object in it, and then figure out what the force is. So it was a useful concept, but it turns out that actually these things are real, because actually electric fields and magnetic fields, they're actually carried by photons. Because they're carried by photons, they're real objects. I mean, they don't carry mass, because photons don't carry mass, but they do carry energy, momentum, and angular momentum, right? And then these fields, they will be a function of whatever configuration you have, right? So you have some electric field that's going to be a function of what charges you have, and then a magnetic field that's going to be a function of what the currents are. But it's important to realize that the way these two charges interact, or the way that, let's say, there's a current carrying wire here, and then there's another current carrying wire here. The way that these current carrying wires interact is by shuttling photons back and forth, which means that because it takes a finite time for photons to make it across from here to there, there's no action at a distance. It always needs to be carried by things that move at the speed of light. All right, so that's the principle of no action at no instantaneous action at a distance. There's another thing that you should realize, and that is that if we have a magnetic field and we've calculated the magnetic field and figured out a magnetic field for, let's say, a current carrying wire, or we figured out the electric field for some kind of a charged object, then if we put another charged object right next to it and we figured out the electric field due to that charged object, or we take another current carrying wire and we place it right next to it, we can treat these independently and first figure out what the solution is of the B field due to this current, and then the B field due to the other line, and then we can just add them, because Maxwell's equations, which we'll get to in a little bit, are linear, right? So there's a superposition principle. What that means is that therefore these photons that are shuttling back and forth, they cannot bounce off each other, right? And they cannot bounce off each other because they are bosons, right? So if these were fermions, then that linear superposition principle wouldn't hold. So it's important to realize that those things are intimately related. Now, generally speaking, if you have, let's say, you have some kind of a charge object rho, and it's stationary, then that usually will give you some kind of an E as a function of r and time. Now, if you don't have a rho that is stationary, but instead you have a rho that is moving, so therefore you get some kind of a current density, then you get a magnetic field. Now, this should already tell you that B is a purely relativistic phenomenon, right? Because if you have a stationary charge, it's E, and then when you start moving it and there's no other charges, now you all of a sudden get a B field. That means that it has to do with the fact that this thing is moving. Okay, so later on we will find that even though in the beginning we're describing the E field and the B field as two separate fields due to either charges rho or moving charges with a current density J, at some point we'll say we'll combine these two into a field tensor F, and then mu nu or whatever, we'll get to that later. And the components of this will be carrying the information of both the electric field and the magnetic field. So we'll combine those later. All right, now we're going to be using Gaussian coordinate systems. Gaussian coordinate systems just make life a lot easier for courses that get a little math heavy. So first of Maxwell's equations in the Gaussian system is, of course, Gauss's law. So Gauss's law says exactly this thing, right? So you have a stationary charged distribution rho, and then that gives you the electric field through this differential equation. It is a little unfortunate that we always write these things in this manner because causality is sometimes lost. I really don't like writing it this way, but it's just one of those things that a lot of people do. I would prefer to say, put the 4 pi rho on the left-hand side and then say 4 pi rho equals the divergence of E, because then it's clear that rho causes E. But sometimes, it's useful to say, it's equal with an arrow pointing to the left. So this thing causes that thing. Okay, now that's Gauss's law in the Gaussian system. Okay, so Gaussian system. Okay, so that's Gauss's law. Talks about the generation of an electric field by a static component. Now, next one, it's Ampere Maxwell. That's describing the generation of a magnetic field through current, right? So there's a current, there's a 4 pi over C, there's a J, or a time varying electric field. Where's my time varying electric field? And if you want to do causality, you do it this way. And this is, of course, that's Ampere Maxwell. Okay, now this is the real current. This is what we sometimes call the displacement current. This displacement current was the addition that that Maxwell made to Ampere's law. So before, Ampere's law was just this, and turns out that there's a vector identity that cannot be satisfied for magnetic fields if you don't add this. So Maxwell saw that, and then so he added this term to it. And the nice thing is that this term is actually the thing that makes electromagnetic waves possible. So all of a sudden, by realizing there was a vector identity that was violated, he added a term to it. All of a sudden, out came optics, which is cool. Okay, so of course this is so this is the generation of magnetic fields through current density. So that's this process, right? So if you have no electric field, no otherwise electric field, just charge is moving, but the charges are neutral. So for instance, they're stuck in a wire, and the wire itself is neutral. You have only current density, and that current density is going to give you this B field. So that's the way that that works. Then I don't like writing them in this form because it's, I don't know, it's weird, but it's what this book does. I usually like writing this one last, but it is what the book does. So next one, it's the curl of E, right? So take the cross of E. Now that's the curl of E. Usually, when you start electricity and magnetism, we'll say that this is 0, and that means that the electric field is a conservative field. But if you have a time-varying magnetic field, it is no longer 0. It is -1/c dB dt. And so it's the circuital law, or Faraday's law if you include this one. And causality goes this way again, right? So you get some time-varying magnetic fields, and then that causes an E field. Okay, and then finally, we have the divergence of B, which is 0. And even though it's kind of a big deal that it's 0, I don't think that nobody actually ever named this thing. So you'll find it as just no magnetic monopoles, which is not really a name that you can give to an equation, but all right. That's what it means. I would call this Gauss's law for magnetism if you want. Now, this is only talking about the generation of electric and magnetic fields, right? So charged objects that are moving, time-varying electric fields and time-varying magnetic fields. These are all generating fields, and that is kind of the final thing that you need to use to figure out what these how these fields are behaving. But we haven't actually talked about how these interact with charged objects. Okay, so if you want to do that, then you actually need the actual force. So it's some charged object moving through an electric field or placed in an electric field plus whatever velocity you have crossed with B, and that is, of course, the Lorentz force law. Sometimes, and I usually do this, I'll call this the Coulomb force because it's only talking about electrostatics. And then we'll call this the Lorentz force times Q. So this would be the Lorentz force over Q. But in this book, we'll combine them both as a single force. And again, that makes a lot of sense because we should really treat electric and magnetic fields on equal footing. So it doesn't really make much sense to pull them apart that way. All right. Yep. Okay. So traditionally, these are Maxwell's equations with source terms, and what we mean by source terms are externally driven source terms. So this is a source term, right? And this would be a source term. That's a little bit of a misnomer, right? Because a time-varying magnetic field is also a source term because it induces an electric field. And a time-varying electric field also induces a magnetic field. But nevertheless, we call the equations without these two terms, we call them the sourceless, Maxwell's equations. And then finally, the superposition principle I already mentioned. So for instance, if you have some kind of a row that causes an E, and then you have another row that causes another E, then you can split this out. So let me show what that superposition principle looks like. So for instance, you can write, E is 4 pi, and let's say we have two charge densities. Then that's 4 pi rho 1 plus 4 pi rho 2. And of course, 4 pi rho 1 is the divergence of E1 plus the divergence of E2. And that is the divergence of E. So therefore, E is E1 plus E2. Okay, so superposition principle works. These things are linear in rho. This thing is linear in J, so that's all good. Okay, now the superposition principle immediately leads one to wonder, okay, what is the best approach of for inverting these equations? And hopefully you'll have had a whole bunch of practice with that. So there's, of course, there's direct integration. So we know, for instance, if rho is a point charge or some kind of a spherical charge object, we know that that's going to give you a field that goes like 1 over r squared. So if you can describe a charged configuration as a sum of point charges that are spread out over space, all you need to do is do a sum over all those charged objects, and then you get the field, right? Because due to the superposition principle, you can just add all of those terms together as long as you factor in all the distances correctly. You can do the same thing with J, right? So if you have some kind of a current carrying wire or a loop or something, and you know what the field is due to that, then afterwards you can add more wires to it and you can get the magnetic field. So you can do that, and you can either do that through summing of terms or direct integration. And both of those allow you to basically work from here to there, because otherwise it's solving the differential equation. All right. So we've talked about the fact that the superposition principle implies that that the photons that are being shuffled back and forth are bosons. So we talked about that already. Okay. So let's start talking about symmetry a little bit. So we know that if we move the coordinate system, these descriptions just move along, right? So if we move this charge 1 meter to the right, but then we also relabel those electric fields by moving the field 1 meter to the right, this equation will still hold, and that's because all of these equations are translationally invariant. Now, the translational invariance So the translational invariance implies that linear momentum is conserved, right? So momentum conservation. We're not talking about accelerating charges, right? We're just comparing two quasi-static solutions, one charge here and then a charge a little bit later. And if it's moving in some kind of a uniform fashion, that translational invariance then translates into momentum conservation. We have a similar invariance. We also have time shift invariance, right? Time shift or time translational invariance, and that means that there's that energy is conserved, right? So energy conservation. Now those are two specific equations, two specific symmetries with a corresponding conservation law. And the general argument is always that if you have some kind of symmetry, then that usually implies that there is a conserved quantity. And that's basically Noether's theorem. And I believe some other people had already kind of figured out that that was a thing, but he, I think, was the first one to actually state it explicitly. Okay, then there's rotational symmetry, or so we can actually rotate the coordinate systems. And that means that angular momentum is conserved. Okay, and now this is the time where we start using nearpod. So, so let's talk about mirror symmetry. Mirror symmetry. I'll put Maxwell's equations here again. So we have divergence E equals 4 pi rho, and then we have the curl of B is 4 pi J over C plus 1 over C dE dt. Over C dB dt. This is your riveting TV, I know. All right. Okay, what do we mean by mirror symmetry? So by mirror symmetry, we say, okay, do these equations give us any indication of whether the coordinate system prefers going from left to right or from right to left? And of course, the answer is no, it doesn't, because we can say, instead of letting the x-axis, for instance, go from left to right, we can actually make it go from right to left. And as long as we make appropriate changes in the electric and the magnetic fields, everything should be all right. So let's see what we mean by having things go in the opposite direction. So let's say we move the, we swap the x-axis, right? So that means that if we swap the x-axis, that means that this partial derivative in the x direction goes in the opposite direction, because now we're not taking a ddx with x going to the right, but we take a ddx with x going to the left. But it should still relate to the same charged object. So we can fix that by not only changing the sign, because we have a nabla operator here, but we also change the sign of E. So the mirror symmetry basically means that if you take E, R becomes minus E minus R, right? So as long as we swap the both the sign of the coordinate system and the sign of E, then the equations will be fine, because we're still talking about the same physical object of rho, right? So it really shouldn't matter how we label the axis, right? Because the electrons, they don't really care whether the axis is running from left to right or right to left. It just knows that there's some kind of a charged object there, and it knows that it needs to respond in some fashion because there's an E field there, and that's the E field that it responds to. So as long as we do this, everything is fine. Okay, so that's what happens when you do this with the E field. Now this is where we do nearpod. I am going to start the nearpod. Hang on a second. So yeah, this is rather tricky, right? So the question is how do we get there? Well, we're changing. We're changing. Let's say the we're inverting the axis, right? So let's say we're changing the x-axis, right? So that means that through here, right, we know that the sign of E is going to change. But we also know that the nabla is going to go in the opposite direction. So actually, there's going to be two minus signs here. which means that B actually doesn't change. Does that make sense? Yes, it does, because it's also consistent with this, because it's 0, right? So we could do whatever we want with this on this side, but it is also consistent with Maxwell too. So we're inverting, let's say, the x-axis. That means we're changing the sign of this one. We're also changing the current density, right? Because the current's now flowing in the other direction, not really the other direction. It just looks that way because we have the x-axis going in the opposite direction. So the sign of this thing changed, right? But the sign of this thing also changed because the nabla operator is going in the opposite direction. So therefore, this sign cannot change. Okay, so we go from B of R goes to B of minus R. All right. We had about 50% of you had that right. Okay, let's look at what's happening with time reversal symmetry. Oops. So time reversal symmetry, meaning we're going to let time run in the other direction. Can we in any way rewrite these fields such that that the equations will be identical? So therefore, we will not be able to tell whether time is running forward or backwards. This one's a little tricky, but so you have to look at what's happening on this side and what's happening on this side. If you were to start here, because that's the first one that actually has a time dependence here, it's a little tricky because you also have the current density here. But if you start here, then you don't really know what's happening, right? Because you don't know what's happening with B, but you also don't know what's happening with E. So you might be inclined to think, well, okay, I can adjust both B and E simultaneously, except how do you know which one you're doing correctly? So it turns out actually it's easiest to start here. So what's happening when you have time running in the opposite direction? Well, we don't know what's happening with the E field a priori, but we do know that the current density would be going in the opposite direction. So that means under time reversal, this term picks up a negative sign. So that means if this term picks up a negative sign, this term as a whole also needs to pick up a negative sign. Now, we're already reversing the time here, so that's already 1 minus, which means that E cannot change. So E, I should use, well, might as well use a different color. Okay, so time reversal. So E, where we have R and T, becomes E, where we have R and minus T. So we're not actually changing the sign of E. So that's interesting. So now what's happening with the magnetic field? So we know that the electric field doesn't change sign under time reversal symmetry. So therefore the left side of this expression doesn't change. So the right side should also not change. But because time's running in the opposite direction, B also needs to change sign, because otherwise these two minus signs won't cancel to make sure that the E field doesn't change. So B does change sign. So we get this one. And you see that it's exactly the opposite of when we do mirror symmetry. Okay, so we've done time reversal symmetry, we've done mirror symmetry, we've done rotational symmetry. Now, of course, there's another big symmetry, and that is the relativistic or Lorentz invariance. Now, we're not actually going to describe these transforms, because these transforms are the subject of an entire chapter. But it's important to realize that these equations allow for it. So what do we mean by relativistic and Lorentz invariance? It means that these laws will look identical independent of which inertial coordinate system you are, right? So if you're riding in an elevator and it's riding smoothly, you'll find the same set of equations will describe electromagnetic phenomena as one where you're not riding in an elevator. But but then that's just Galilean invariance, right? So Galilean relativistic, sorry, that's a tongue twister, Galilean relativistic invariance. Now, Lorentz invariance actually is very special. It's not just saying that all inertial coordinate systems are the same, so therefore these equations should look the same. They should also all hold and give you the same speed of electromagnetic waves. And of course, that is true, right? So that's a subject of an entire of an entire chapter, and we will get to that later. Now, let's talk about the duality in E and B. So let's call these sourceless terms, right? So sourceless terms. So sourceless, sorry, Maxwell's equations. Hang on. All right, so yeah, so sourceless Maxwell equations. So we have our Gauss. We've got curl of B is 1 over C dE dt. And then we have the curl of E is minus 1 over C dB dt. And then we have divergence of B being 0. Now, hopefully you see that these equations look very similar to each other, right? So look at what's happening with the E field. So divergence of E, sourceless version of Maxwell's equations, is 0, right? So divergence of E is 0, but also the divergence of B is 0. So we could swap E and B here and have the exact same expressions. We could do the same thing here, except we would have to change the sign, right? Now that seems to indicate that we can just describe everything with either electric fields or magnetic fields. So why are we treating electric fields and magnetic fields differently? Well, that is because there are no such thing as magnetic monopoles, but there are, of course, electric monopoles. Now, I should, for completeness' sake, say that there is there's this thing called the Valentine's Day monopole, where people sitting under a mountain were trying to figure out where, they're trying to see if they can detect magnetic monopoles. And there's this one specific signal, a little blip, and that seems to indicate that there could be a magnetic monopole. But if it is there, then it is exceedingly rare. And every day that we're running such detectors and we're not seeing any, we're increasing the certainty with which we can say that for any kind of real purposes, in our universe, it doesn't look like magnetic monopoles exist. Okay. Now that's the symmetry that we can swap E and B. What was the next one I was going to do? Yeah, charge conservation. Charge conservation. Okay, so charge conservation. You've probably seen this equation before, but looks like this. So it's minus d rho dt. Why does this thing express charge conservation? So it's also this expression is also called the continuity equation. Continuity equation, and it's actually the hang on a second. Yeah, I got my signs right. Okay. it's easiest to see that this expression describes a charge conservation by converting these two into their not differential form, but integral form. So what we'll do is we'll say, okay, let's take the volume integral of this thing. So we'll do so minus. So we'll take the integral, the rho dt. There's no vector, obviously, and we're integrating that over volume, and then we're doing the same thing on this side. So we're integrating this over the volume, and of course these volumes have to be the same, and then we can swap these two. We can swap these two, so we can just say it's minus the time derivative of the integral of rho dv. Okay, and this we can use. I keep forgetting Green or Stokes. I think it's Green's theorem, where you can change this into a surface integral, where you're just doing j dA, where this is now the normal that is pointing out of a surface that is wrapped around this volume integral. Okay, so this is the integral over the edge of the volume, and that volume is this volume. So these two integrals, they're linked to each other, they're not independent. And this is a surface integral, and that's a volume integral. This is the volume integral over some kind of a Gaussian object. So it's a three-dimensional object. It's got a well-defined inside and an outside. And because it has a well-defined inside and outside, it also has a well-defined edge. So therefore, we can unambiguously describe the normal pointing out. Okay, so now why does this describe charge conservation? Well, look at what's this saying. This is the current density. This is the current density that's integrated over surface area. So in other words, this is the current that is flowing out of this volume V through the surface A. Okay, so this is I out of that volume V. Okay, so this is the total current that's flowing out of V, and then this rho dV is actually the total charge enclosed in V. So I that's flowing out of V happens to be minus ddt of the Q that's in V, which makes a lot of sense, right? So you have some charge enclosed in some Gaussian sphere, and then that changes as a function of time. And the only way that it can change as a function of time is if there's a current that's flowing out of that volume, because otherwise spontaneously charge would be appearing or disappearing. We can't have that because charge is a conserved quantity. Okay, so that's why we're saying that this expression says that there's this continuity equation expresses charge conservation. I believe at some point later we will actually derive this equation. You've probably seen this before, but it's already buried in Maxwell's equations. It doesn't take too much work to show that. All right, so let's clarify the units here a little bit. So first of all, this is shorthand. The dA vector, that's actually, so let me, let's say I'm going to draw this object. Okay, so this is V, and then this is a patch of a surface. It has size of dA, but it also has a normal. That's the normal. And then I'm using the normal times dA as shorthand for dA vector. So that's the first thing. Now, current density is, it's the units of current density are amps per square meter. So if you, let's say you have a wire, or you have some kind of a wire, and there's a current that's flowing this way, and it's got this kind of a surface area, unfortunately A and A. This is ampere, sorry, this is ampere, and this is surface area, let's call that A in square meters. And if the current density is uniform, then that means that J here is just whatever the total current is divided by the cross section of the wire. So this, That's what we mean by current density. So therefore, if we take the current density and we integrate it over area, we're at every infinitesimal section here, we're going to get current times d area. So if you integrate that, you're going to get current times area, sorry, current density times area, and therefore you're going to get current. All right. Now, let me see, we talked about that. We talked about the interaction. Yes, okay, so last one, waves. So you've probably seen this, but let's do this anyway. Starting with Maxwell's equations without sources, find the wave equation for E. All right. All right. Well, let's see what we did. So remember I said start with sources, Maxwell's equations. So divergence of E is 0. Curl of B is only that 1/c ddt of E. That's time varying electric field. That's the displacement current. Faraday's law without any J term. So there's that gives you the Faraday's law, right? And then Sorry, the J term is here. And then finally, of course, there's no magnetic monopoles. But now you see that these four equations have, again, this very nicely symmetric form. So if you want to get the wave equation for E, you got to figure out a way to eliminate B, right? So you should all know by now that if you take a d b dt, that's going to give you an E. And if that time is then time dependent, that's going to give you a dE dt, that's going to give you B. So if you want to get the wave equation for E, you got to figure out a way to eliminate B. Now, in order to eliminate B, you see between these two equations, this one is just a straight up ddt of B. This one is the curl of B. So what you want to do in order to eliminate these is you want to make these two terms look more like each other, right? So why don't we take the curl of both sides? So we take the curl of, here we go. Yeah, take the curl of this. And therefore, we also get the curl of the dB dt. And of course, we can swap these two terms. And now we have the curl of B. So therefore, this term now looks like this term. So we can eliminate the curl of B in favor of the dE dt. So that's the right-hand side. Now, the left-hand side, you needed this identity. So this is a double derivative identity that you should know. You should have some kind of a cheat sheet somewhere with a list of things that if you have two Napa operators with crosses and dots, it's usually in one of those forms. There are ways to express it in different forms. So in this case, you get a curl of E, and that's known as the gradient of, in parentheses, the divergence of E. Now the divergence of E in this case, because it's sourceless, there's no rho term here, so this is 0. So the gradient of 0 is obviously 0. And now you have minus Napa operator squared of E, and I already replaced the E here. So now we have minus Napa squared. E is, I believe I have a extra minus here somewhere. Yeah, I have an extra minus here somewhere that I'm not supposed to have. I'm not sure where it came from, but I'll fix that. And now you got your wave equation. Let me see if that's correct. So, yep, that's correct. That's the wave equation. Now, of course, this Napa operator squared has a shorthand, and that's the Laplacian operator. So it's also minus 1 over c squared, and then d squared e dt squared. And that's your wave equation for E. Ta-da! That's pretty, isn't it? Now, those of you that have done wave equations with me when we were doing this in Physics 226 know that it was a lot more work. It was usually like 2 whiteboards full of approximations and Taylor expansions, but now we can actually do it this way because there's just a couple of identities that we need. Those of you that have a bit of a hard time keeping up with this stuff, this is really where I need you to be for the rest of the semester, at least as a starting point. So revisit this, and let me see. Yeah. Okay. So let me look you in the face as I'm saying this. So yeah, this is you should be able to throw these vector identities on the paper. It shouldn't take you too long to put these together. Getting the wave equation like this is that's straightforward physics 410 material. Some of the symmetries you might have not seen in this manner before, but they're, in terms of math, they're not complicated, right? You can see what happens when you just have time going in the opposite direction. You can see where the signs are changing. So it just requires you to look at the equations a little bit more carefully. And then, of course, we'll go into all of the physics of all these phenomena the next few chapters. But a big one we still have coming up, and that's, of course, that's chapter 2. Now, chapter 2 is what we'll start with on Wednesday. Yeah, so 2 days from now, and that's where we'll start going through all of the math stuff that you will need in addition to stuff that we've seen so far. Just a refresher on where you all need to be. Any final questions? Okay, we're all good. Excellent. Okay, thanks. See you, everybody.